Hey, Rock Buzz Rock Papa here. Hope you guys are doing great. In our last video, which was a while ago, we talked about ocean crust and what ocean crust is made of. And I showed you ocean crust in Papa's little rock world. Today we're going to talk about land crust, what it's made out of and how it comes to be, and what are the petrological components of land crust. So, here we go. Okay guys, remember in our last video about ocean crust, we said that ocean crust is made of gabbro, which is on the bottom here. This is actually meta-gabbro, but I'm pretending it's gabbro. And above that you have basalt. And above that you have, not only above that, but all mixed in with it, you have serpentinite. Okay, so these rocks are loaded with iron and magnesium. There's also calcium, which is the white stuff. Iron and magnesium are heavy elements. That's why ocean crust sinks down below land crust. And land crust is made of granite and other rocks that are low in iron and magnesium and high in silica. That makes them lightweight, and that's why land crust floats or buoys up above ocean crust. Okay. In my mind, this idea of ocean crust and land crust brings up the question, what came first, ocean crust or land crust? And how did land crust ever form? That kind of tells you that ocean crust came first. There is a quasi-scientific text that says, in the beginning the earth was without form and void. That's an accurate depiction of the earth when it was just a big ball of gas. So as the surface of the earth began to cool and the gases coalesced into something more solid, the earth got an atmosphere. Actually got several atmospheres over time. Earth's first atmospheres were very toxic to human life. One toxic atmosphere succeeded another, and these atmospheres formed a kind of an opaque vapor that surrounded the Earth. And then eventually, water dominated the atmosphere. And as this text to which I refer continues, the water separated into water above the earth and water on the earth or below the earth. And then you could see the sun. The sun had been there the whole time, but it was not visible because of the water vapors, etc. So oceans came first, and ocean crust came first. Ocean crust is really just the top, the cool top of the mantle. You know, the mantle, as we talked about earlier, is made of dunite and peridotite. Most of the entire earth is made of dunite/peridotite, and it's very heavy. That's why it sinks down low. But rocks like gabbro, basalt, serpentinite, diabase, they're not quite as heavy as the peridotite, so they float above it, and that's what forms ocean crust. And by ocean crust, I don't mean if you go down to the bottom of the ocean, you've got sand and mud, and so that's not ocean crust. That's the stuff that's on top of the ocean crust. So back to the question, how did the first land crust get here? So let's talk about this scenario. In the early days, I don't know, 4 billion years ago, plus or minus, the earth was cooling, the mantle was cooling, but it still was absolutely boiling, bubbling hot, and all these convection currents were moving around in it, just like, you know, if you're boiling a pot of water, convection currents occurs because the water next to the burner heats up, gets hot, expands, and moves upward, that sort of thing, and that was happening in the mantle. Back in those days. It's still happening, actually. So all this convection, heat convection that was going on in the mantle caused some parts of the mantle to be super much harder than others. and those hot parts began to expand up and bulge and crack the ocean crust that was above it, creating a rift in which more ocean crust was made. So you've got this ancient 4 billion plus or minus year old rift in the ocean crust. New ocean crust is being produced and pushing out ocean crust on both sides of this rift in the ocean. So now let's go to the other side of the world. Since rifting is occurring and you're getting more and more ocean crust on the planet, the diameter of the planet doesn't change, so all that extra ocean crust has to go somewhere. And so you get a piece of the ocean crust busting on the other side of the world, and that piece dives down, is pushed down underneath the other piece of ocean crust. That's subduction. Now here's where the strange thing happens. A lot of seawater goes down into the subduction trench with the piece of ocean crust that goes down there. And that ocean water facilitates a process called fractional melting. So here's how fractional melting works. The hunk of ocean crust, which is made of gabbro, basalt, serpentinite, maybe some diabase, is pushed down below the other piece of ocean crust, and it dives down deeper and deeper toward the mantle, and it begins to melt. And a lot of ocean water goes down with it. And then something happened that the ring did not expect. Quartz has the highest melting point of all the major rock-forming minerals, maybe 1,700 degrees Celsius. But the water that goes down into the trench with the subducting ocean crust causes quartz to melt at the lowest melting temperature of all the major rock-forming minerals. And so quartz and potassium feldspar melt first from this ocean crust mix that's melting. And the quartz and the potassium feldspar rise up and push up and start forming a stratovolcano that's part of a volcanic island or a volcanic island chain. This felsic tough material, it's molten. It goes up and it cools and clogs the mouth of the volcano. Next, granite melts out of this mix. Granite is quartz, potassium feldspar, maybe a little sodium feldspar, muscovite, and a little bit of biotite. It comes out of this mix, melts out and rises up and butts up against the bottom of the felsic tuff that's plugging the volcano. Next, rocks with intermediate compositions melt out. I mean rocks that are high in biotite, hornblende, and sodium feldspar. We're talking about diorite. Diorite magma rises up and butts up against the granite that's beginning to cool, the granite magma that's beginning to cool up there. And this is not a description of the exact process, but it's a description that will help us remember how it works. Finally, all that's left is mostly what's left is the gabbro magma down there. Okay, but more and more ocean crust is subducting and creating tremendous pressure down below. And that causes magma to erupt as lava on the surface of this volcanic island chain. At the very top, what might happen is the felsic tuff might explode out of the top of the volcano, rain down upon the underwater sides of the volcano, creating sedimentary rocks. And then the granite magma might erupt in forming dacite lava and rhyolite lava. Down below that, on the sides of the flanks of the volcano, the diorite would erupt out and form andesite lava. And then down toward the bottom, the gabbro would erupt, forming basalt lava. So you get a stratovolcano that's a mixture. When you have subduction, you get stratovolcanoes forming that are a mixture of felsic intermediate and mafic magmas and lavas. Now, this process that I've just described happens over and over as subduction continues. In other words, the felsic tuff blows out of the volcano, the granite magma erupts as dacite and rhyolite, the diorite erupts as andesite, the gabbro erupts as basalt, and then it happens all over again, so you get this layered effect like an onion going on. Okay, now we'll continue. And these comprise the new land crust. But that is not the end of the story. And to see more of this story, we're going to go to Papa's Little Rock World. Grammy really loves this. Okay. So, we're going to put together a volcanic island chain. We better be like this for now. A stratovolcano. Actually, we're going to put it together. We're going to start off with its magma components. Down at the bottom of the stratovolcano. Stratovolcanoes, by the way, are products of subduction. We've got gabbro. Gabbro magma. Gabbro is made of pyroxene and calcium-rich feldspar, maybe a little hornblende. Mafic. Above that, you've got diorite magma. Diorite is made of some quartz, not much. Sodium-rich feldspar, biotite, maybe a little hornblende. And we're doing the core of this volcano, the interior. Above that, you've got granite, magma. Granite is made of quartz, potassium feldspar, a little bit of sodium-rich feldspar, biotite, and muscovite in small amounts. And then above that, you've got a big hunk of felsic tuff that's plugging the volcano. And you can look at this felsic tuff, it's kind of pinkish. And that tells you that it's made of quartz and potassium feldspar. Let's get a little close so that we can see the quartz hunks in here. See the gray quartz hunks in this felsic tuff. And it's also got a lot of air pockets in it. It's pretty light. You could call it pumice, which is a very lightweight felsic tuff that's blown full of air pockets. So here's the core of our stratovolcano. Now pressure continues to build because subduction continues, so that several things happen. One thing that happens is the gabbro magma erupts out onto the surface as basalt lava down low on the flanks of the volcano. Okay. And then you have the diorite magma erupting maybe midway on the flanks of the volcano as andesite lava. There's two kinds of andesite lava. Andesite can be gray or reddish, even very dark. And then the granite magma is going to erupt into felsic lava. And we have two kinds of felsic lava here. We've got dacite lava. It's actually metadacite, but I don't have any dacite. Dacite lava is made of quartz. You can see gray quartz in there. Potassium feldspar and some sodium feldspar. No biotite usually. Maybe some muscovite, but I don't see any. And then this is trachyte, which is a felsic kind of lava. And this came from Idaho. Trachyte is made mostly of potassium feldspar and some quartz too. Pressure continues to build. This felsic tuff blows out of the volcano. You have to have that sound. And it breaks up into all kinds of fragments. The fragments settle on the underwater flanks of the volcano as sand and mud. But that's not the whole story. That sand and mud gets flushed through by hot volcanic vents that flush iron and sulfur into it, creating a metamorphic rock called quartz, muscovite, pyrite, sericite, schist. In this example, the white stuff is sericite, which it happens when muscovite is exposed to water. The brown stuff is either iron, most likely it's iron staining. And you can see some little patches of shiny muscovite that's turning into sericite. A lot of this stuff has a very red cast to it. Let's see if I can find some down here. This is some, nope, yeah. Isn't that a gorgeous specimen? Quartz, muscovite, sericite, pyrite, schist. Beautiful stuff. You can see the reddish pyrite staining. Well, that happens when the felsic tuff blows out of the volcano, settles down on its flanks as sand and silt and mud, and that material is flushed through with the volcanic vents that bring up sulfur and iron, etc. There you have it. Papa's little rock world stratovolcano material. And this is the stuff that begins to create land crust, but that's not the whole story, because eventually that volcanic island chain is going to crash into either another volcanic island chain or a continent, and that is a collision event, and collision events cause metamorphism of all these rocks. So next time we'll talk about what happens to these land crust rocks when continental collisions occur. And just by the way, we talked about how ocean crust is made mostly of mafic rocks. Land crust is made mostly of intermediate rocks, but there are also a lot of felsic rocks there too. And we'll talk about those in the next episode. Anyhow, thanks for watching. And this is your Rock Papa. Papa out.